Good afternoon, everyone. So my name is Miriam Leeser. I'm a professor at Northeastern University, and I'm talking about joint work with Michael Zink, who's at UMass Amherst, and our students. So Shayan Khan, who's here, is one of my students at PhD student at Northeastern, and Kalyani Patel, who's at UMass Amherst. So I'm interested in two themes that you've already heard about. One is, what does the future of a data center look like? And the other is, I'm an FPGA person, so I'm very much interested in accelerators and how to use them efficiently. So we've been looking at, especially in the context of the Open Cloud testbed, security and the whole notion of disaggregated data centers, and then the role that these network-attached FPGAs play in that. So the general data center model is that you've got a bunch of nodes, and the nodes are connected to a network, and basically the processor is directly connected to the network, and you have accelerators hanging off of the processor, or your memory hanging off of the processor. And to me, that's sort of the old way of thinking about cloud computing data centers or whatever. So the new model that a lot of people are looking at is this notion of disaggregation. So what that means is, instead of thinking of nodes and allocating nodes to users, that you have banks of memory, you have GPUs, you have FPGAs, and all of those things can independently be on the network. So it allows me to more efficiently allocate resources. So for example, if Mike has an application and he wants to use 2 GPUs and I just want to use the FPGAs, we could use the same nodes, but the hardware could be allocated differently to different users, just completely based on what their needs are. It also means that my traffic can get processed straight off the network. It doesn't have to go through the CPU and then to the accelerator and back. So the original idea behind disaggregation was about memories. Let's take the memories and basically put them with the memory controller on the network, not initially tied to the CPU. Now we're breaking that apart even more and saying that I have a pool of these different devices and each of them can be allocated independently. And this is a conceptual model, really. I can still build my network just like I always did. I can still have my racks with accelerators and things like that on the processor, and that's typically how they're there. But if I attach them directly to the network, now I have this, I can think of everything as this disaggregated model. Okay, so in the Open Cloud testbed, that's pretty much what we're doing. So you may not have seen this picture if you've been here both days. You've seen this a number of times. This is all the different racks in the Open Cloud testbed. Like I said, I'm an FPGA person, so the piece that's on the bottom left is where the FPGAs are. And we have 16 Xilinx Aviator 280 FPGAs, and they're each allocated in a host. But what's unique about the setup that we have is they're also directly connected through 200 gig Ethernet connections to the switch. So I can directly send traffic to and from an FPGA onto the network through the switch. That's not so unique, but what's unique about OCT is we let users program these. So the user can directly program. So there are other instances where people have done this, but it's all in-house, and there's no public resource like Open Cloud testbed that allows me as a user to play with this. So we have a build environment for creating your design that's separate, and then we have the Open Cloud testbed with these FPGAs where I can launch and conduct my experiments. So one example that we've been playing around with in my lab is everybody's favorite example, machine learning. I can get better models if they're bigger, so I run them across multiple hosts. They talk directly to one another across the network. The processor sends off the initial data and gets the results, but all the intermediate thing is done direct FPGA to FPGA communication. So the other thing we're interested in, since we're exposing this to the user, is the programming model for the user to program these FPGAs, and for this we're using P4. So P4 is well known in the networking community, and so we're allowing people to write P4 programs and offload them onto the FPGA. So I can program data plane components onto my FPGA. I'm not going to spend too much time on this. This is just the sort of architecture of a P4 model, which is matches and actions. But we have a framework that's built on what a number of other people have done. So we're using various tools, mostly from AMD Xilinx, so something called the OpenNick Shell, ISNet P4 that allows you to compile and download your P4 programs and put it on the FPGA. And you'll notice on the slide the two gray regions, that's where user logic goes. So if you write your own program, it gets compiled into, we're actually using the middle big box for your design. So if I look at this closer to our setup, on the Open Cloud testbed with these P4 enabled, basically what it ends up being is a smart NIC. It looks something like this. So I can directly communicate over the network. I can program my networking function on the FPGA. We support externs, so if you have mathematical functions or other kernels that you want to implement that are outside of sort of the P4 tool flow, you can run those as well. So we support this box of externs. And once again, we have 100 gigabit per second. Okay, so that's sort of the whole setup, right? OCT, FPGA is directly connected to the network. People can program it with P4. So I started off by saying that we were interested in FPGAs and security. So what does any of this have to do with security? So basically, this gives you all sorts of advantages in terms of efficient use of your accelerators and getting to your data and running things quickly. It also exposes a new attack surface, basically. Because now I'm letting a programmer have direct access to the network with a device that's not running an operating system. So I can't put any sort of network checks on it. And I'm letting it do whatever it wants. And the interesting thing is all the tools I talked about are open source, which is great, right? I can get them, I can run them, I can customize them. It also makes them a lot easier to attack. So open source is wonderful, but it also exposes another attack surface. So what we've been looking at is, with this framework, what kinds of attacks might you expect from the network level? And then what can you do about it? So like I said, I'm an FPGA person, so I think the FPGA is both the problem and is the solution. So I'll talk about both of those rules, right? So the first one is basically, I can program one of these devices to just sit on the network and flood the network. You can just sit there and send out packet after packet after packet. Okay? So it's really, really easy to launch a denial of service attack. So that's the FPGA being the attacker, but it doesn't have to be an FPGA. Any device that I'm directly connecting to the network could potentially launch such an attack. So what about the security aspect of it, the second half? So how are FPGAs part of the solution? And here's where that whole P4 role comes in. So we're looking at, given I have these devices on the network that are potentially have malicious behavior, can I put an FPGA on there that essentially monitors the network and detects that there's something malicious going on and identifying who that potentially malicious user is? So what the second FPGA on the left is doing is it's programming security functions. So it's basically snooping on the network, if you will, and trying to detect possible, malicious behavior from other users on the network. And the reason there are two yellow boxes there is we support runtime reconfiguration, which means you can swap out the security functions you're supporting based on whatever's happening at a given time or what you might want to do. So I don't remember if I have a slide for this, but one of the applications we're looking at is implementing heavy hitter detection on the FPGA, so you can tell on the network if someone is basically doing exactly what it said, which is blasting packets out. The other model, so that model is coexist with everybody, let everybody do whatever they want but monitor. And the other model is prevent the malicious behavior in the first case. So in that case, we're giving the user less freedom to do whatever they want. We're putting a layer that's essentially a security layer, maybe a firewall, maybe heavy hitter detection before the network connection, and then allowing the user to have less freedom, but stopping the attack before it starts. And we're looking into basically both of those models. So like I said, one of the first things we're going to play around with is what's called Aviator Detection. This is not new. The reference is actually to someone else's paper. But basically, this is something we can implement on the FPGA. An earlier speaker talked about sketch-based algorithms. So this is also a sketch-based algorithm that's hardware friendly. And we plan to use that to monitor the network and try to identify malicious users. The Cloud Lab gives us, one of the freedoms it gives us to do is to actually launch these attacks. So I forget what I was talking about yesterday, but there are also very few networks that allow me actually to do security research by attacking the network. But I get an isolated piece of network, so I can launch a denial of service attack and then see if my solutions work, which is really, really nice to have discussion. Anyway, to wrap up, I have all these nice resources through the Open Cloud testbed, and we are providing FPGAs directly connected to the network, which enables disaggregating resources, which can both be the source of my problem, but might also be the solution. And we're looking at that. So we're looking at implementing what I basically talked about, network monitoring and secure operations to prevent malicious behavior on OCT. So that's the proposed research. And I do want to say that we're also trying to replicate a lot of what we're doing in a lot of the other systems you've heard about. So Fabric, Chameleon, OCT, we all have the same FPGA, so we're trying to copy things across different networks. Although I don't think Fabric would like it if I launched a denial of service attack. So with that, thank you. If you're interested in more details, we have a poster outside, and I'm happy to answer